Okay, let's begin, everyone. This is the daily summary. Okay, there's a signature sheet that you want to pick up for your team. And I have, as mentioned in my email, have assigned report 2 problems. And here I'd like to remind you that for the file names, please use this format, okay? So that it's uniform for everyone and also easier for the TA to look at your report. So IEA S15 spring 2015 team number, and then the report number, and if you do individually, then there's the last name coming after that. Yes.
Is this going to be due on Wednesday next week?
Thursday.
Okay.
It, you know, the deadline is in the problem statement. Okay, so and you know, I'm flexible up to a certain point. If you need more time, just let me know.
Question.
Directly.
Is that for like participation points?
Sorry, say that again.
How does it work? Like, what does that count?
That's it. Sorry.
Like, how
I'm
does
sorry. You need to speak louder. Oh, that's the in-class assignment. Yes.
Okay. So like, if you miss one, what happens?
Well, you know, it's part of the in-class assignment. It's, you know, in case there's justification, then just let me know. Yes. All right. Let me. Yes, and Michael has been preparing this document where you would see the best solution, the best reports for this semester. That is built on top of last semester. Oh, I also want to mention the following regarding report 2, just like for report 1, to continue to develop you know, good communication of ideas and facilitation of learning. I have posted in the resources the best reports and best solution from last semester to serve as a study guide for you, and please try to do the problems without looking at these best solutions and best reports, and you would look at these only in case you get stuck and would like to get unstuck and move forward. Also, I'm available as well as Michael, the TA. So please use all of the resources that is made available to learn. And that's what it means by facilitation of learning, right? And regarding the best solution and best reports, you can look into this document and see that Michael has already listed here for this semester, so Team 6. And so he will post Team 6 reports in the resource folder for everyone. Let me see whether it's available yet. So it would be in the best overall reports. Yeah, so here. And Michael, you may want to also make this uniform, use the hyphen instead of the underbar. The hyphen or the minus sign will be less work.
Would you open it real quick?
Sorry?
Can we see it just real fast?
Yeah, I'm going to show you. You. All of you have access to this. So this is the report from Team 6 here. Okay, and so you can go through, you know, there's a comment from Michael. Okay, and this is available for everyone to see. There's no grades here, there's only comments. So, and you can see the very nice work is done here. All right. Oh, one thing that I'd like to mention, and And this is to avoid plagiarism. Whenever you use something that is not of your work, do give a reference. If this is taken out of my lecture notes, refer to my lecture notes. Okay. Or any other reference you pick out. So if you did not create certain things, did not write, then give reference. Okay. So that's regarding the best solutions and best reports. And I have posted here a number of references related to the last lecture. First, a very nice article about Newton, like I said. Newton was also an alchemist trying to transform metals, ordinary metals, into gold. And this is in relation to the statement that Euler formula. Euler found gold through a feat of mathematical alchemy. And that was a saying from the a set of documentary called The Story of Math. Okay, and as I mentioned before, I think I have written here. This is my annotated notes from last time, and I wrote down here. This famous. Let me zoom in. This formula, which was declared as the most beautiful formula in mathematics, and the reason it's beautiful because Euler was able to unify three famous quantities, right, E, I, and phi, into a simple formula, right? And there's a saying by Einstein that says that a good theory or a nice theory should be simple but not simple. Simple but not simple. Okay, so that's regarding this article, and I have also a number of references that hopefully would inspire you. And this is a very nice talk on YouTube about Euler. It's a very beautiful talk. And how about? And there's several other references. Oh yes, this book here, 17 Equations That Changed the World. You will read about the story of the imaginary unit, square root of -1. And there's a book review here. You will see why it was one of the most important relation that changed the world. Okay. The other two references are also very nice: Men of Mathematics and Women in Mathematics. Okay, so that's, and I'd like to finish up section 53C. There is not a lot left, and move on to motivate the eigenvalue problem. Okay, so 53C right here. Yes, like I said, we have gone through a lot. We have already done all of this. I have already mentioned that you can transform from a seemingly complex valued function for the displacement, okay, into a real valued function. And I give a reference here, right here. Okay, a very specific reference. That's in my section 6 lecture notes, where you can read about Euler formula and the transformation of the homogeneous solution from complex valued function to real valued function. And there's also the video of my lectures related to that. Section 6. Okay, so to wrap up this section, so and the method was by introducing kappa 1 and kappa 2 as complex constants, okay, and through some alchemy you can obtain this expression. where a and b are real numbers, okay, and cosine and sine functions are also, of course, real valued function. And here is just to refresh your mind that minus alpha square is omega square, and omega is square root of beta if one defines beta as minus alpha square, because beta is strictly positive and omega is square root of beta. And you will see that beta would be called the eigenvalue, and so the circular frequency of vibration is the square root of the eigenvalue. Okay, so that's the explanation. So now I would like to really move forward and give you a more concrete feel of what it means by eigenvalue. Okay, no, this is by eigenvalue problem, eigenvalues and eigenvectors. Okay, so let's see. I have prepared my notes here. So here we will focus on this part. Okay, motivation for eigenvalue problem. So I take a simple 2 degrees of freedom system, spring mass, no damper, and with 2 ends fixed, okay, and with uniform spring constants. So let me go to my notes. And I should have, I will shuffle maybe I should move all of these down. So I have space for, let me move over here, next page. Okay, so let's take a simple system very similar to what we have been doing. 3 springs, so it's also 2 degrees of freedom. Right, so see. Get this out. Okay, 3 springs, 2 masses, 2 ends fixed. All right. Now the spring constants are equal, so make it simple. Let's say they are equal to 1. K2 equal to 1. K3 equal to 1. So this is not the first time you have seen this. I have also solved even more complicated problems, which is problem 1 in the exam, 1.1. So this is basically a review, if you like. So this is the just to show the origin of the displacement. Okay, so we have the displacement d1 and d2. And let's consider static. Okay. And then you have the applied forces, F1 and F2. And let's say, just to give some numbers, let's choose F1 to be 3 and F2 to be -4, just to show that these are algebraic quantities, right? So it means that if the force value is minus, then the actual direction is just pointing to the negative direction. That's all. So here every direction is in the positive direction, and these are algebraic quantities. And with that, I go back to my notes and I put the minus here. Okay, because I started with +4, but I thought, well, it's good to show the students to what it looks like when you have a minus force, right? So now, what would be the stiffness matrix and the force matrix? Any contribution? This is a good opportunity to contribute here. You would have now, of course, you don't have the equation of motion, but you have the equation for statics, right? There's no inertial force, no damper, so there's no md double prime, no cd prime. There's only kd equal f, right? So maybe it's good for me to remind you that the general equation of motion is md double prime plus cd prime plus kd equal to f. Okay, and now this is static. So, and let me note down here, this is static. Right. Then clearly you would not have these, and also, yeah, static is enough, because if it's a static problem, there's no damping, so we can eliminate the first two terms. So the kd equal f. It's just like the spring, the force displacement for the spring, right? Force equal to spring constant times displacement. So this is just general in the matrix case. So contribution, anyone for active learning credit? Excellent. Could you speak louder? Hang on. Let me get my sheet here. Record. Yeah, excellent. So, what's your team number? Team 1. What team number?
3.
Team 3. Yeah. What's your name? Blake. Team 3. Okay, I got it. Yeah, go ahead, Blake. What would be the expression for the stiffness matrix K?
2, -1, -1, 2.
Excellent. So Blake said the expression for K would be 2, -1, -1, 2. So K. Okay. K equal to 2 minus 1 minus 1, 2. And let's recall how you get that, okay? This is very important. And so you need to review the formula that Blake already applied. This is the street fighting method here, right? And so the first row corresponds to the first equation. That's essentially F1, and the columns is really D1 and D2. Okay, so for this coefficient here, that corresponds to, if you multiply, there would be D1, right? You multiply by D1 and D2. So this coefficient would be multiplied by D1. This one would multiply by D2 equal to F1. So the first row corresponds to the force F1. And so for the coefficient that is multiplied by D1, it's in between the two springs, so therefore you have the sum of K1 plus K2, that's equal to 2. And for the second equation that corresponds to the force F2, this coefficient would be multiplied by D2, and that D2 is between two springs, so K2 and K3, so this is K2 plus K3 equal 2. And the coupling between D1 and D2, there's a spring K2 in between. K2 equal 1, so minus K2 minus K2. Okay, so that's a quick review there. So Blake left an opportunity open for someone to contribute. What would be the force matrix? Come on, quick. This is the force matrix. The expression for F. What would be the expression for F? Okay, so I see Kevin asked. Could Kevin and Mark give, what is your name?
Right.
Let me, I try to bring in new people. So what team number?
7.
Team 7 and Frank.
Yes.
Okay, I remember now. You were the one who asked about the videos.
Yeah.
Right, so Frank, very good Frank. So what is the expression for?
Is it going to be 3 over -4?
Yes. So Frank said F is equal to 3 and -4. Okay. So to solve for D, you need to invert K, right? So here, if you have a matrix A, so D, let me write here. D is equal to K inverse times F. Okay. And now if you have a matrix A which has the coefficient A, B, C, D, okay, then the determinant of the matrix A is, let me move forward. So there's a lot that I'd like to do, so I will take more contribution later. AD times BC. Okay, and this is not memorization. In my mind, there's a very clear process, but I just don't want to get through that now because that's a very beautiful theory of matrices. Okay, from that you can write. Okay, it involves minor and major submatrices. So here I just want to enunciate the formula. So the A inverse would be 1 over the determinant of A times D A minus C here and minus B here. Okay, so we can check. In my mind, I did the computation, not memorization like I mentioned to you. So let's check. Let's take this. Okay, let me do like this. Let's take A inverse. Multiply by A quickly. And that would be this matrix here. Times A, which is this one. In your case, it's sufficient for you to remember this or write in your formula sheet. That's fine. I wish I could have time to teach the matrix theory, but okay. So now, what's the result? Let's write the result. Let's do this matrix multiplication in here. Right, so we have D times A, that's AD. Minus BC, right? Minus BC. So that's in the 1-1 position of the matrix. And look at the 2-2 position, meaning take row 2 times column 2, right? Again, you have minus BC plus AD. So again, in this 2-2 position is AD minus BC. Okay. And now let's look at the 1-2 position, row 1, column 2. So take this row 1 times the column 2 of the second matrix. So you have DB minus DB, okay, so 0. And the 1 position, row 2, column 1, so take row 2 in the first matrix, minus BC, 2, 1, so row 2, column 1, so minus CA plus AC, so that's 0, okay? And AD minus BC is the determinant of A. So therefore, the result is that you would have the identity matrix, right? right? And that is a verification of that indeed the expression that I gave you is the inverse of A. Okay? And you can also verify that A times A inverse is also the identity matrix I. Okay, this is all right. So now we have the formula for the inverse. You can easily invert this matrix, and you multiply by F, you get the solution D1 and D2, the displacement. All right, that's not a big deal for everyone, right? And so that, let me move forward to Wolfram alpha. If you have questions, please ask. Okay, I'd like to move forward, but I don't want to move too fast that I lose the audience. Okay, so what I did in Wolfram alpha here is I code up this matrix. Okay, so let me let's see, Control plus to see whether, yeah. So you know the this is how you code the matrix 2 minus 1 minus 1 2 using the curly brackets, and I gave you the code in the lecture summary and also the link to this. If you click at the link, you would see this immediately. And again, like I said, please do not sign until the last 5 minutes, okay? So that you can collaborate before you sign. And so if you look through this, you know, Wolfram alpha give you, let me walk you through. Okay, so first you type in the code, then you need to verify the input to make sure that Wolfram alpha interpreted your code correctly. And if you see something wrong in the input, you know that your code was not correct. Okay, so here it looks like my code was correct, 2 minus 1 minus 1 2. And let's see what it gives you. It gives you the plot. Well, this is just the plot. It thinks that, well, these are the coordinates of 2 points, you know. So this point here has the x equal to minus 1 and y equal 2. And this point here has x equal 2 and y equal to minus 1. So basically it just plot that. That's nothing interesting there. And then you see two rows, 2 columns, and then the matrix plot. But now you begin to see something something that may or may not be familiar to you, right? The determinant. The property is symmetric, and there's more. We don't get into that. The trace, we don't get into that. But the determinant, you know. You can verify that the determinant of this matrix was 3, right? Using the formula that I just mentioned. Right? AD minus BC, that's 3. There's a characteristic polynomial. There's the eigenvalues, eigenvectors, and then diagonalization. Okay, diagonalization. And you see that in this diagonalization here, let's focus on this part. You see that you start with the matrix M, and then there's a matrix S, and then this is a diagonal matrix 1, 3. And the inverse of S. And this diagonal matrix actually contains the eigenvalues. There are 2 eigenvalues, lambda equal 1 and lambda equal to 3. Okay, as written up here. I say lambda, but this is the notation here. Okay, lambda 1 equals 3, lambda 2 equal 1. All right, and then I'd like to ask you to keep in mind, yeah, the inverse. You can verify that the inverse is this, right? Using the formula that we have. So let me demonstrate to you. Why don't we just do it quickly together? You see, from this formula here, determinant is the determinant of the matrix K, right? If you want to invert K, you need to find the determinant of K. Right, and that's by multiplying the diagonal coefficients and minus the product of diagonal coefficients. Right, so 2 times 2, 4, minus 1 square, that's 3. Right, so from this formula, you have that the determinant of K is equal to 3. So that verify with Wolfram alpha there. And all you have is just to use this formula and plug in the right coefficient, right? So therefore we have the inverse of k. So note here. So you have 2 minus 1 minus 1, 2. And if you follow this, then 2 is A, and 2 down there is D. B equals C equal to minus 1, right? So the inverse. The determinant of the matrix K we already have, that's 3. So you have 1 over 3. D is equal to 2, so you have 2 here. A is equal to 2, you have 2 here. B is minus 1, so minus 1 plus 1 plus 1, right? So that's the inverse. So let's write down the inverse of the matrix K right here. So K inverse is 1 over its determinant, and using what I just said, that's 2 plus 1 plus 1. And you can verify by multiplying K with its inverse to make sure that you have the identity matrix as shown here. And if you look into Wolfram alpha, indeed the inverse is 1/3 times the matrix 2, 1, 1, 2. Okay. That explains that expression. Now let's go back to diagonalization, and this is what I'd like to use to motivate the eigenvalue problem, right? Remember that, as I said, how do you solve this system? Let's see, we must have, this is the, to solve the coupled system, we need to look at the undamped free vibration. Right, so this is the coupled system here. You see, you have two ODEs that are coupled. And if we look at the static problem, you remove the inertial force, remove the damper force, and you have only this part. Okay? Now, uncoupling, you want to diagonalize. Right? So very much like the mass matrix. This is not a diagonal matrix. The damper matrix, the damping matrix, and the stiffness matrix is not diagonal. So the goal is to diagonalize, and the method is using the eigenvalue problem. And so I like to illustrate this idea using the eigenvalue problem just for the static case. Okay? How to solve for the eigenvalues, we'll look at that later. But for now, let's accept the the result and then verify. Okay? So let's recall the matrix K. Okay, we call K instead of M, Wolfram alpha. Use a notation M. So this is K here. And let me put the expression for K down here. And it has two eigenvalues as the result of Wolfram alpha indicates for you, but I would like to change the order a little. I call lambda 1 equal to 1 and lambda 2 equal to 3. Okay, I just reverse the order because in dynamics, the lower eigenvalue corresponds to the lower frequency, and that corresponds to called the fundamental vibration frequency. Okay, and the higher frequency would have smaller amplitude. So the role of the lowest eigenvalue is very important. Okay, and using our notation, the eigenvectors would be denoted by phi 1, and that has 1, 1, and phi 2. Okay, phi meaning phi with the underbar is 1 minus 1. Okay, instead of minus 1, 1 that you see here, and you'll see why. Okay, so first, what does it mean, eigenvalue problem? Right? What is an eigenvalue and eigenvector? So you take K, you multiply by phi 1. What do you get? Right? So K times phi 1 is this matrix here times the matrix, the column matrix that has 1, 1. Okay, and that gives you what? Let's work out very quickly. Let's give you 2 minus 1, that's 1. And so minus 1 plus 2, that's 1. What do you see? You see that when you take k multiplied by phi1, you get back phi1. Okay, exactly phi1. Right? This is phi1. And you can think of it as a scalar 1 times phi1. And this scalar 1 here has a name, that's lambda 1. That's the first eigenvalue. Alright? Now let's try the next one. Let's take k times phi2. So k times phi2 is very similar. Okay, let me remove the index here. And so phi2, and phi2 is 1 minus 1, right? So if you work out, what do you get? You get 2 plus 1, right? 2 plus 1 equal to 3. And then the second coefficient is minus 1 minus 2, that's minus 3. Okay? And if you pull 3 out as a common factor, you get 1 minus 1. So what you see here is when you take the matrix K times its second eigenvector, you get the eigenvalue, the second eigenvalue, which is 3. That's lambda 2 times phi2 times the eigenvector itself. All right. Okay, so what it says is the following. So here is the definition of the eigenvalues and eigenvectors. So if you take k times phi1, then you get lambda 1 times phi1. Okay, that's for the first eigenpair. An eigenpair is the eigenvalue and the eigenvectors, okay, and the corresponding eigenvectors. And for the second eigenpair, essentially you just remove the index 1 and replace by 2. That's all that is. So k times phi2 is equal to lambda 2 times phi2. All right. So now let's let's define.
Is the phi2 and the phi1 on the left side of those equations, are those supposed to be underlined?
Sorry.
The phi1 and the phi2 on the left side of those equations, are those supposed to be underlined?
Yeah, phi1 they must be underlined. Yes, that's the matrix quantity. Yes, thank you, Kevin. There must be an underline here. That's the matrix quantity. Okay. So I give Kevin team 7. Deep learning credit. All right. So now let's introduce a new matrix called gap phi. So this is capital letter and with the underbar to designate a bold-faced letter, and define that as the matrix phi1 in the first column and the matrix phi2 in the second column, right? So if you write down in detail, that would be 1, 1, and then 1 minus 1. Okay. So you see that this matrix here is very similar to the matrix S in Wolfram alpha. It's just that the sign here, the minus sign is down here, that's all. Don't worry about that. They are the matrix of the eigenvectors. Okay. So so now what you want to do is to combine both of these two equations, K1 phi1 equal lambda 1 phi1 and K2 phi2 equal lambda 2 phi2 into a single matrix equation, right? And that single matrix equation reads as follows. So you have the matrix K times this matrix. Now it's a 2 by 2 matrix with the two columns, right, phi1 and phi2 side by side. And so what would that be equal to? That would be equal to phi1, phi2 times the matrix of the eigenvalues. That's lambda 1 times lambda 2. Okay. And you have 0 and 0 here. All right, let's try to put in the number so that you can understand better. You know, K, we call that K is this matrix here. Okay, that's 2 minus 1 and minus 1, 2. Now the matrix big phi that has two columns, phi1 and phi2 is right here. Okay, so that's okay. So now you have the equal sign, and for the matrix of the eigenvalues, that would be what, 1 and 3, right? And the off diagonal coefficients are 0. Okay. So if you multiply out, you should see that the two sides are equal. Okay. You can verify because it's basically just a rewriting of what we did up here. For example, for K2 times phi2, it's just this is K times phi2 is just this matrix K times the second column, right? And that would be equal to when you multiply this matrix with this diagonal matrix, what's the effect? When you multiply this, you see that the first column here would be multiplied by the first eigenvalue, right? Because when you take this row times this column, this is 0. So the second column does not matter, right? When you multiply with the first column here. So take this row, 1 times 1, 0 is equal to 1. And then take the second row, 1 minus 1 times 1, 0 is 1. So what you get back is the first column. And for the second column, you take 1 times 0 times 3, that's 3. And then 1 minus 1 times 3 is minus 3. And that's exactly that one. So it's the same, but combined into both. You get the same result as these two separate matrix equations into a single big matrix equation. Okay. So what does it buy for us doing that? Okay, this is a very beautiful result here. What you can write is the following. Okay, let's introduce the matrix notation big phi. So you can write K times big phi equal to big phi times lambda. Okay, where this is K, right? And this matrix here is big phi, the matrix, the underbar, and this is the same matrix big phi here. Okay. this is the new matrix that I call lambda, capital lambda, and that represents the matrix of the eigenvalues. Okay. So with this expression here, you can. So how do you? How would you diagonalize k? You know. So there's two ways to do. Let's post multiply this expression by k inverse. Okay. So what I meant is the following. Let me do this. If you multiply, post multiply meaning multiply from the back, from the end, by phi inverse. Okay, this is phi inverse. So on the other side, you also multiply by phi inverse. Okay, now phi times phi inverse is identity, right? So you see that now you can already write k. The result is that k can be written as this one. And there's a diagonal matrix in between. Okay. Now it turns out that phi inverse has a very nice property. And this is a property of the eigenvectors that you want to keep in mind. Okay, so let's recall that phi, the matrix big phi here, is equal to, yeah, actually I can copy the whole thing, so I don't need to copy again. Let's recall that phi can be written as this one. Right, and that is essentially the first. Remember, the first column is the eigenvector phi1, and the second column is the eigenvector phi2. Okay. Now, what is the relationship between phi1 and phi2? Thank you. Let's look at phi1 dot product with phi2. Okay, what is phi1 dot with phi2? You have the dot product between these two column matrix or vectors, right? 1 times 1 plus 1 times minus 1, 0. So that means that these two eigenvectors are orthogonal to each other. Okay, so the orthogonality of the eigenvectors is very important. This is equal to 0. So you write we say phi1 is orthogonal to phi2. Okay, that's the orthogonality among the eigen vectors. And one can show that there's a simple relationship for the inverse. Okay. But with the time, okay, we have 2 minutes, so I'll continue next time. We already found here a diagonal matrix. That's the beginning of the uncoupling. Okay, so next time I'll show you how to use the uncoupling to solve the system.
Whatever gets us out 5 minutes early.
Just read down this message a little bit so I can
Yeah, biomechanics and materials lab right up to Monday night.
Yeah.
And that's going to take a lot of time. Yeah.
Absolutely.
This is due Thursday, I think?
Yeah.
Alright, yeah, we got
You just want to compile it.
I'm open to whatever else.
Have an awesome weekend, all right?
Yeah, have a good one. Probably.
Oh,
See you guys later.
So I guess you end up with like a fraction of 1 over R C S is 1, right? Second, yeah. Just do 4 to 6. Yeah. Or no, 6:30. It was like I didn't think about that until I had already started. How did you like from a whole loss maybe? Like I didn't see because the numbers were like S squared plus like 40 plus like 1400 or something. Yeah. Like I don't know how you convert it. See, that's what I did. I didn't know this said give it.
Oh, you put like